Okay, so what I'm going to talk about is how you can actually write serverless and do serverless applications using JAX-RS and Jakarta EE, which is the new name for Java EE. So in the keynotes this morning, there was a lot of talk about all of the considerations that you have to think about and implement when you're building cloud-native applications and deploying to platforms like Kubernetes. And if you saw the last of the keynotes, Sebastian talked about how he sees the future, including serverless, or the present if your companies like Netflix and Amazon building at scale. So what I'm going to cover is a little bit about what serverless means, the difference between functions and serverless, and then I'm going to spend maybe 5 or 10 minutes demoing how you can actually build serverless applications using JAX-RS to build HTTP REST APIs, get it deployed to Kubernetes, and have all of those considerations around observability and metrics and monitoring and security and resilience dealt with for you. But we're going to start with what is serverless. So is anybody here actually doing serverless development today, doing functions with Lambda or no? Okay. So this is kind of a typical chart that gets put up when people start talking about serverless. And on the vertical axis, you have the simplicity of building applications, right? How easy it is to write business logic. And on the horizontal across axis, you have what it takes to actually then get that deployed into a cloud. And we generally have this arc, which starts off talking about virtual machines and things like OpenStack in the bottom left-hand corner, where you bring everything. And in the top right-hand corner, it talks about function as a service and serverless. And the idea is, if you're doing IaaS, you're doing virtual machines, as a development or an operations team, you need to build the entire stack. Right? You create a virtual machine. You might be doing Docker inside those virtual machines. You have a Java EE server. If you're doing Java, you have to configure that. You then actually bring your application, and on top of that, the last stage is to actually have your application code and your business logic. If you're doing things like Kubernetes or container as a service, what you have to bring is a Docker container with a configured server, with an application, and then your business logic. If you move to something like platform as a service with things like Cloud Foundry, the simplicity goes up another layer. You have to bring a Java EE server that's been configured. You have to bring an application and then your application logic. And in some PaaSes, they've kind of moved that abstraction layer up one further, so you don't need to bring a server, but you do need to bring a WAR file or an AIR file. And then what FAS says is function as a service says you don't need any of that. You just bring functions. You bring application code, and the rest of that is provided for you. How you take those functions, how you expose HTTP endpoints is dealt with by the function as a service platform. So does that mean serverless and function as a service is the same thing? Well, it depends who you ask. So if you ask Wikipedia, and this is Wikipedia's summary of what function as a service is. Wikipedia says it's something that provides a platform that enables you to run and manage functionalities, application functions, without the complexity of building and maintaining the infrastructure. So that sounds like serverless. But it also says this is one way of achieving serverless. So FAS is one type of serverless, but it's not the only type of serverless. So as it's only one way, what this tells us is FAS is just one form of serverless, because FAS is actually two things. It's about simplified dev and deploy, and it's about simplified infrastructure and scaling. So we had those two axes, and those two axes are actually different things. So if you take servers as you have to build everything in the bottom left-hand corner, at the top of that left-hand scale is actually doing function development, where you just write application code, something else knows how to configure a server, put it in a Docker container, getting it running in an orchestrated cloud. And then on the other scale, this is where serverless comes in, which is now that I've built that server, how do I deploy it at scale and have it automatically scale out and scale back in again so that I don't actually have to worry about the operational concerns. So FAS is both functions and serverless, which is why it's one type of serverless. Now, that means that you get both simplified dev because of I don't have to build the stack, and I get simplified operations because when I deploy it, I don't need to worry about how it's scaled and how it's configured. So FAS gives you simplified dev and ops, but you can do these things individually. You can have functions programming, but actually build a VM or a Docker container and manage it how you like. Or you can do scaling, and you can actually do serverless scaling of full Docker containers without doing functions. So FAS is both serverless and functions. So let's look at the use of functions as a service with Java. So look like not many people here are doing function as a service. How many people here are doing Java at least? Right. Okay, so almost everybody is a Java developer. So the fact that you're not doing functions may be because hardly anybody is doing functions in Java. So this is the breakdown of usage of AWS Lambda, Amazon's implementation of function as a service. And you'll see the top usage is Node.js. Actually, the third usage is Node.js, and so is the sixth. So these are just different versions of Node.js. I mean, in fact, 67% of all usage on AWS Lambda is doing Node.js. Second comes Python. So again, 3 entries for Python, different versions. The most is at 16%, the next is at 9%. But this is 26% of the usage of AWS Lambda is doing Python. Java comes in third at 3.4%. So why aren't people doing function programming in Java if they are in Node, if they are in Python, if they are in other languages? Well, some of it is because of the scalability model. So if we look at another type of function as a service, this one, OpenWhisk, which is an Apache open source project. And as an open source project, it becomes easier to see how it works. The scaling model that exists for OpenWhisk is there's one action, one request, one container. What this means is, let's say I have a user that wants to make a request of a service that I've implemented using functions as a service with OpenWhisk. What happens when I make that one request is it actually starts a Docker container that has an OpenWhisk runtime in it that provides an init and a run endpoint, and then your application code sits at the top. And it's one action, which is my function, one request, one container. So if I have a second user that wants to make a second concurrent request, what happens for that second concurrent request is I have a second container. So every request gets its own container and its own function applied and its own execution. And the side effect of this is, if you have concurrency, if you have many users trying to use your thing at the same time, you have a scalability problem due to startup. Right? Every time there's a request, if I don't have one of these ready that's just fallen idle, I have to start a second container. So startup time really affects the performance of functions that you write. So this is the startup time for Express.js, which is the most popular framework in Node.js. And it takes about 0.5 seconds to start up, handle a request, and have that request actually visible back to the user. If we compare that to Spring Boot, Spring Boot takes about 13 seconds to do exactly the same task. And this is because we have to start a JVM. We have to do all of that dynamic loading. We have to ready our endpoints. We have to dynamically load our code, and then we can actually serve the request. So everyone's using JavaScript. No one's using Java. Now, there are other frameworks that try to slim things down and make it faster to start up. So Thorntail is one of them. That takes about 8.7 seconds, but that's still unreasonable for any kind of like web request or HTTP endpoint or REST API where a user sat at a desktop or on their phone is accessing that API. An extra 8 seconds of latency is just too much. So this is where frameworks like Quarkus come in, which I think there's a few more sessions on over the next 2 days. What Quarkus is trying to do is really improve the startup and the memory footprint for running Java applications with a full implementation of the Java Jakarta EE spec. And the side effect of what they've done is they kind of tried to remove a lot of the dynamic nature out of Java so it can start quickly because it doesn't have to do lookups. And the effect of that is Quarkus can actually start in 1.6 seconds. And this is running on a full Java JVM. Now that's still a little bit slower than JavaScript and Node.js, but it's much, much closer. Now, there's also Quarkus using native compilation, which is using the Graal VM, which I think there's another couple of sessions on over the next 2 days as well. And this pre-compiles your Java code to build a native binary. And native binaries don't have to launch a JVM, so they're significantly faster. And in fact, Hello World on Quarkus starts in 0.1 seconds. So suddenly, with frameworks like Quarkus running natively compiled, we have the ability to start almost instantly, and in fact start faster than the most popular languages in serverless. So that's one part. We can fix the startup problem. The next part, has anybody here heard of Knative? Anyone? Okay, so Knative is a new project. It stands for Kubernetes Native. And one of the things that it provides is the ability to run full Docker containers in a serverless mode. So that was the horizontal axis of take a container, Knative will worry about how to scale it. Now, when this is the concurrency model that you have for normal FAS platforms, one request requires one container. Knative is very different. What Knative does is it says, if you have one request, I have to start a container. And Knative doesn't know what that container is. You can bring any existing application that you can put in a Docker container, you can run in Knative. So on the first request, it starts that container, which because of things like Quarkus, we can start in 0.2 seconds rather than 13 seconds. But one of the differences is, if I have 100 concurrent users, they can all use the same container. And this is because Knative says, I'm just running a container. You're going to bring your own framework. And Java frameworks are very good at handling concurrent requests, so why not let them do that? So between 1 and 100 concurrent users, I can reuse the same container. When I have 101 users, I do have to start a second container. But for all the way up to 200 users, I still only need to have 2 containers deployed. So what Knative will do for you is it will add containers according to usage, the amount of concurrent users. And if you have no users, it just removes all of the containers. So it scales out on request and scales down to 0 when there's no requests. So between Quarkus and Knative, we can actually now do serverless Java, but you have to bring an entire Java application. So what about how to do functions on top of Knative? And that means have that simplified programming model and have it run on something that knows how to do security and metrics and observability. Well, so let's look at the function programming model to begin with. And this is, again, OpenWhisk for how to do Hello World. What OpenWhisk does is you implement a class and you give it a function called main, and that receives a single thing, an object, which is a JSON object. So it's expecting to receive JSON. And it returns a response, which is JSON. So OpenWhisk's API is single JSON object in, single JSON object out. And that's deliberate because it's the only API it provides, and you can use functions to do many, many different things. You can use it to do a batch job execution. You can use it to build REST APIs. You can use it for anything that you like. And the programming model is very, very similar for AWS Lambda. AWS Lambda, you write a class, which is a handler. You put a handle request function in it. This takes 2 parameters. One is a payload, and the other one is a context. So it's very, very similar. It's a generic API because it's designed to allow you to do anything. You'll also notice that these are 2 implementations of function as a service, but their APIs are different. And one of the concerns that people have when they adopt function as a service is they are currently all proprietary APIs. So there's a risk of vendor lock-in. If you start writing applications to AWS Lambda or Azure Functions or Google Cloud Functions or any other set of functions, you're buying into an API that's provided by that platform. And you cannot then move it somewhere else. Let's compare this to what people are using functions for. So this is the new Stacks serverless survey from last year. And they asked people who are writing function-based applications what they're using them for. The number one use case, 73% of people are building REST APIs. Interestingly, another 26% said they're building mobile backends, which are typically REST APIs. So there's a huge amount of usage of functions to build REST APIs. But we're all Java developers here. And if I'm writing a REST API in Java, I might use something like JAX-RS. Now, JAX-RS gives me domain-specific APIs. It knows I want to build a REST endpoint. So it gives me the ability to set the path I want to run on using @path. I can talk about whether it produces JSON output or text output. It will parse the headers for me. It will parse the URL for me, give me parameters and so on. So we've spent years in Java building APIs that help you actually implement things that you want to do. And therefore, you get domain-specific APIs. Functions are designed for you to write code that can be used for anything. So it has a very generic API. One parameter in, one parameter out. Or in Lambda's case, a parameter and some context in, and one parameter out. So if you want to build REST APIs, it's actually easier to do it with a set of APIs that's designed to help you build REST APIs. So this is where Appsody comes in, which is what I'm going to demo for you. What Appsody does is it allows you to compose applications from pieces. So it provides a CLI that lets you do the full life cycle of building an application. It provides a number of stacks. You can think of these as when we went through IaaS, CaaS, PaaS, FaaS, each of those abstracted away some of the stack that you have to build. And Appsody actually supports all of those layers. And then it provides the ability to deploy it to Kubernetes. Now, those stacks work at 3 levels. We have what we call cloud packaged. This is you bring your application, right? Whether that's something like Quarkus or Spring Boot with your APIs and your application code, and it will take it, create Docker images for you, and deploy it to Kubernetes. At the next level, which we call cloud native, it provides a pre-configured server that has metrics and observability, security, and so on built into the platform, so that you don't need to know how to do those cloud native capabilities, or you can build these stacks yourselves with the capabilities that you want, and then you just bring your code on top of it. And finally, we have the same thing for functions, which is what I'm going to show you in a second, which means you can just build things like JAX-RS endpoints in your application code, and it will do the rest of the work to get it deployed into Kubernetes for you. So at that, this gives you an optimized cloud deployment with you having to do nothing but write JAX-RS. So let's see this actually live. So is that actually readable by everyone, or should I go a little bit bigger? Let's try bigger anyway. All right. So Appsody itself lets you build a whole bunch of different application types. And this is a 100% open source project available with an Apache 2 license. So it's got support for Quarkus functions, but you can build Node applications with loopback. You could do Node functions. It's got support for Vertex, Rust, the Swift programming language, pretty much anything you can think of. So to create a new project, I'll create a new directory, go into that directory, and then just do Appsody init, and we're building a Quarkus function project. Now, that is going to do 2 things for you. It's going to build you a very basic project structure, and it's going to bring you a copy of that cloud runtime down onto your local system. And one of the reasons that we do that is as you develop, you can actually develop inside the same thing that it's going to run on when you deploy it to a Kubernetes cloud. Now, once that's initialized, I can then open the project. I'm doing this in VS Code, but you can use any IDE that you like. It doesn't seem to want to come up cleanly, so let's try that again. There we go. And I'm going to have to make this bigger. Okay. So I'm just going to do an Appsody run whilst I explain what's in the project. So what Appsody run is doing is it's starting a Docker container for your project. So you develop locally in your IDE. It mirrors that code directly into a Docker container that matches your cloud deployment. And as you make code changes, it mirrors that into the project and rebuilds it inside the project container. In terms of the project itself, you have a POM XML, which you're going to expect to have because that's how you add your own dependencies and develop as you would normally. And you have a source main and test directory, and there's currently nothing in it. So this is just a blank project that you can start developing from. So what I'm going to do is, just because you don't want to watch me do typos for a while, I've just imported a simple JAX-RS endpoint. Now, the side effect of me importing that endpoint is I've just made a code change on my laptop which got reflected in the container. So if I open my browser and go to localhost 8080 and then go to, we're on /hello, I get my code running. And this is all running directly inside a Docker container. Now, if I go to my project and I make a code change and hit save, and then I go back to the browser and I reload, it's got the code change. So this is exactly the same as if I was developing locally. It just happens to be doing it in a continuous Docker container for me. So if I then go back, I remove that change and hit reload, the change is immediately reflected. So you actually have what's like a local development environment running in a virtual runtime inside a Docker container, and that thing's going to match what you have when you push to production and go into Kubernetes. Now, the fact that you're writing functions and you don't own the full server means that whilst what we're developing looks like a normal JAX-RS project, you get a whole bunch of stuff for free. So this morning, a couple of people mentioned the value of having things called health endpoints. So we implement a health endpoint for liveness, which Kubernetes will use to automatically restart you if you crash or if you hang. There's also a readiness endpoint, which it uses to check whether you should be in load balancing or not, so applications can tell the load balancer it's not ready to receive requests. And you also get metrics. So this is the metrics that is expected by a system called Prometheus. So it's a whole bunch of key value pairs. So it talks about, in this case, say Jaeger tracing, and it has a number next to it. Now, it is human readable, but it's not designed to be used by humans. Prometheus is a monitoring and metric system that builds into Kubernetes that reads this data and puts it into a time series database. So it collects this data and allows you to actually visualize and view it over time. And it's talking about Jaeger tracing because you also have tracing implementation built into the platform for you. So I can develop applications and they're running inside a container. I can also stop that and I can start a debugger. So let's just run that again, but this time in debug mode. Now, this runs exactly the same as it does in run mode. The only difference is it starts it with a debugger inside the container, opens the necessary port inside the container, and configures the IDE so the IDE knows how to connect to it. So if I set a breakpoint, and then I go to the debug view, and I run the debugger, so I now have a breakpoint set on /hello. So if I go back to my browser, and I go to /hello, it triggers the breakpoint for me. So again, it's like I'm running a local debugger, but this is running directly inside the container. So that's all local development, but a whole part of this is about being cloud hosted and having it deal with how it integrates into the cloud and with things like metrics, monitoring, and health for you. So the last thing I'm going to do is I'm going to take this and then I'm going to do a run task and I'm going to do an Appsody deploy. Now, at this point, I've had to do nothing with Docker, I've had to do nothing with Kubernetes, but it's now running in Kubernetes locally on my laptop at the address it's just given me. So if I take this and I go back and I now load that port, and again I go to /hello, my application is now running inside Kubernetes, and I didn't need to know how to do that. Now, the other thing that you get is this is the Kubernetes application navigator dashboard. So it's automatically detected that I've got an application called qfunc, which is my Quarkus function, which is running. It knows about the components of that application, but it also gives me a bunch of actions that I can take. So one of them is to go and view the liveness endpoint. Another is to actually go and look at the metrics. So that metrics endpoint is publishing data which shows up inside this graph. So I can look at things like when the data comes through, the number of available CPUs, the heap memory, and so on. Now, I'll come back to that in just a second, because we also have open tracing. So this knows about every request that has been made of the application and shows me the full details of the fact that it was a GET request, the amount of duration it took. All of the information is provided for me. So this has now detected that my application is running, and it's starting to populate with data. So as we've just hit time, if I go back to the presentation, what we've seen is no one is doing functions in Java today, whether it's Amazon, whether it's OpenWhisk, whether it's Google Cloud Functions or something else. Now, part of the reason for that is startup time. That's been solved with things like Quarkus and Micronaut. Knative lets us then take that and scale it, and Appsody lets us have this programming model where I can just write functions with whatever framework I like, whether that is Quarkus. You can do it with Spring Boot if you want to, but startup times mean that you may not want to deploy it as a serverless application. And then you get all of the integration with the cloud platform for free. So everything that people talked about this morning about the difficulties of building optimized containers such that you know how to layer it properly, you redo caching, such that you have used multi-stage builds to remove components. That's done for you. Things about health and observability and metrics and tracing, that's all done for you. With these three projects combined, which are all open source, you can actually build functions that let you concentrate on writing application code and let the projects deal with how those get deployed and run in Kubernetes. So I'm available afterward for questions, and there's a bunch of stickers here if you want them. Thank you.